Okay, so what you're looking at here is part 2 of a video I'm making about L'Hopital's rule. On this part, I'm going to do the problems that are a little bit harder. I think you'd have to watch part 1 for this to make any sense, but all right, there is a part 1. And then here's where I want to start in part 2. Okay, all right. So take this, limit x goes to 3 of x to the x power versus limit x goes to 0 from the right x to the x power. Okay, now this one, there's no controversy in calculating it. If you want to know what happens when x gets close to 3 for x to the x power, then you can plug the 3 in and see. Okay, 3 to the third power. Is there any difficulty in calculating that? No difficulty at all. That's 27. All right. So this one's uncontroversial. This one is of a form that can't be calculated. Look at this. It's of the form, I don't know, say you put the 0 in. 0 to the 0 power. That's a type of indeterminate form. Originally in the part 1 of the video when I introduced this, I said indeterminate forms are 0 over 0 or infinity over infinity. This is not one of those, but it's still something that can't directly be calculated. We can try if you want. So 0 to the 0 power, and it tells me basically that there's not an answer to that. All right. But it still might be true that I can ask, well, what happens when the x is really close to 0 on the right-hand side? I know you can't calculate 0 to the 0 power, but I know you can do like 0.1 to the 0.1 power, right? Remember, with limits, it doesn't matter. You know, if I want to say what happens as x goes to 4, it really doesn't matter if you can't plug 4 in to that problem. There might still be an overall pattern, okay? The same thing here. I can try to put 0 in and see what I get. Maybe it will work out for me. If it doesn't mean there's not an answer. Okay, so this is also indeterminate, it turns out. But the only method I gave you was this. I said that indeterminate forms were fractions. It was 0 over 0 or infinity over infinity. So we need a way to transform this. Here's how we do it. We call this y, right? That's how formulas normally work. You plug x in, you get y back out. Everything is number in, number out. So we do that first. Then we take the logarithm of both sides, natural log. And we can do that. I've got an equation. If I want to take natural log of both sides, I can do that. I treat both sides the same. I do that because now I have some freedom to move this. There's this rule for logarithms which says the logarithm of a number raised to a power. That power can be moved here as a multiplier. So I get like so. Okay, and then we'll figure out on like this. All right, we'll say, okay, that's the limit we're trying to investigate. Let's do here. Limit x goes to 0 from the right, x natural log of x. Okay. All right, now I had done that one already in part 1. Okay. So I did it right here. It was one of the problems I've done. You can go back and watch part 1. Ultimately, it's 0, okay? So, all right, this limit is 0. So here's what that tells me. If you let x go to 0 from the right, that will go to 0. This will become 0. And then so it tells me that natural log of y is 0. Okay? And then that tells me, well, what is natural log? It's a logarithm with a base number of e. So it says log base e of y is 0. And then that tells me that y is e to the 0 power or 1. Okay? Why is this our answer? Well, because I was trying to work on that to start with. Now I figured out what happens to it. I called it y, all right, when x goes to 0 from the right. The y goes to 1. Okay, so that's how we do that one. If we have like a form 0 to the 0 power, we'll call it y. We'll introduce the logarithm. We'll work things around from there and get an answer. And then we'll solve for the y once we have this number, right? That's what this part is. Okay, so let's try another one that is like that, right? Like this one here. This is a form, it's kind of like that one. All right, let's see. So if x goes to 0 from the right, what form are we getting? Are we getting something that we can calculate in a straightforward way, like this, 3 to the 3rd power? Or are we getting something that's nonsense, like 0 to the 0 power? So if x goes to 0 from the right, that part will be 1. And this part, well, we talked about this before. What happens when you divide by smaller and smaller numbers that are closer and closer to 0? You get a bigger and bigger answer. The smaller and closer is the number you divide by, the bigger the answer is you get. And so this is 1 to the infinity power, which is tempting to think is 1. But I mean, really, if 1 to the infinity power was 1, there'd be like an infinity button. We could just press it and say 1 in power infinity. But again, infinity is not something that we can do calculations with, so this is indeterminate. Okay. So all right, it has an exponent like that one. So my way of working it around will be similar, all right? So here's what we'll do. Our method to solve this limit will be to call, since this is indeterminate, since I can't just plug that number into that, my way of breaking it down will be to call that y. Y is 1 minus x to the 1 over x power. And then what was our next step? To introduce the natural logarithm on both sides of that equation. Okay? And then we do that so we have the freedom to move this power around, which is going to look like this. But then with a little rewriting, this will be natural log 1 minus x over x, right? To multiply 1 over x times natural log 1 minus x, I might as well just write it as a fraction like that. Okay, so it's this thing then, because that is a fraction, and indeterminate forms with L'Hopital's rule, as we've learned it, you need a fraction. You need a form 0 over 0 or infinity over infinity. This is one of those forms. This is an indeterminate form. Okay. In fact, it's one of the ones that I did earlier on in the video. Here we go. It was this one right here. Okay. All right. So say we did that, and I got that it was -1. Okay, it's an indeterminate form to start with. So when you look at this, say limit x goes to 0 from the right, natural log 1 minus x over x, then it'll be like that other question that I did in part 1 of the video, and it's -1. So what does that tell us? I wanted to know what happened to this. Okay, that thing. I know this will become -1, so that tells me natural log of y will be -1, or y will be e to the -1 power. All right, there we go. So our ultimate limit, e to the -1 power, or 1 over e. Okay. All right, so that's how we'll treat problems where it's some indeterminate calculation with an exponent. It'll be like this one or this one. Notice my treatment and all my work, I did it the same way. So let's look at one more type of indeterminate form. infinity take away infinity. All right? Where you would think that, I mean, I guess it would be natural to think that that was 0, but again, infinity is not a number that we can do calculations with. And what you might think by intuition would be correct about infinity often is not true. So if you would think infinity minus infinity is 0, that would be natural and normal, but also wrong. Okay? So look at this. X goes to 0 from the right. What does that look like? Well, so we've talked about this, right? 1 over x, if x goes to 0 from the right, will be infinity. And then what happens to sine x if x goes to 0 from the right? Well, sine of 0 is 0. And the smaller and closer to 0 that x is, the smaller and closer to 0 that sine is from the right-hand side. Okay? So that's also an infinity. That's my point. Okay? Like if you said sine of 0.00001, it'd be a very small positive number, and 1 divided by that would be a very big positive number. So my point is that's indeterminate form, infinity minus infinity. Now I need to turn this into a problem just like the ones we learned, where it's some fraction that's either 0 over 0 or infinity over infinity, and then use L'Hopital's rule as we've already learned it. Okay? The way that I can do that is just to subtract these. Okay, so look, we can do like this. Limit x goes to 0 from the right. We could get a common denominator and subtract these. The common denominator would be sine x. Or sorry, it would be x times sine x. If we combine these, it'll be sine x minus 1 over x sine x. Okay, so now I turn this into that just by subtracting the fractions. So is this now indeterminate? Is this now 0 over 0 or infinity over infinity? Those are the indeterminate forms that we can work with. If I put 0 in, sine of 0 is 0, minus 1 is negative 1. So I get negative 1 over 0. Okay? Oh, I just realized I messed that up. Oh my goodness. If we add these, or sorry, subtract them, we'll get sine x minus x over x sine x. Okay, sine x over x sine x minus x over, okay. Made a mistake, anyway. So, okay, now I get this. Is this an indeterminate form? If I put 0 in, I get 0 minus 0 over 0 times 0. So this most definitely is an indeterminate form. 0 on the top, 0 on the bottom. So it might as well be like this one that we did in part 1 of the video. It's the same form, the same technique. L'Hopital's rule says that now that we have this form, we can take the derivative of the top and bottom and then reapply that limit. So here's what we'll get. I'll reapply to limit as x goes to 0 from the right. Derivative up here is cosine x minus 1. Derivative down there with the product rule is sine x plus x cosine x. Okay? And then I'll try to do this limit again. So, let's see. 0 goes in. Cosine of 0 is 1. 1 minus 1 is 0. Okay, that's fine. It's just 0 over 0 is indeterminate. Just because I got 0 on top doesn't mean I have a problem. But then I put 0 down here. Sine of 0 is 0. And 0 times cosine 0 is also 0. So not only is this an indeterminate form, but I use the rule and so is that. Okay, but if I have this form, I can keep repeating the procedure. So, I mean, just the way it worked out this time, I'm going to have to do this again. All right, so limit x goes to 0 from the right. All right, this is still an indeterminate form. So I can still take the derivative of the top and bottom and reapply the limit. Derivative of cosine is minus sine. Derivative down here, cosine, plus, by the product rule on x cosine x, I'll get cosine x minus x sine x. So there's the derivative of that bottom part. F prime is 1 times g is cosine plus g prime is minus sine times x. All right. Now hopefully this is not an indeterminate form anymore and I can get my answer, but if x goes to 0 from the right, sine x is 0. And down here, I'll get 1 plus 1 minus 0. So I'll get 0 divided by 2. 0 divided by 2 is 0. All right. So if you thought, well, it's like, no, obviously 0 or infinity minus infinity is 0. We did all this work and got an obvious answer. Well, I'll show you this one. Like, we cannot assume infinity minus infinity is 0. It's not how it works. Calculations with infinity are very tricky. So I have another example. You could pause the video right now and try to work that one and see what you get. Or do it the same way as this other one. But I just want you to see another one so that you don't leave this thinking, why bother with all this? Because anything minus itself is 0 is obvious. It's silly to go through all that. Well, okay, it's not true here. Okay, let's look at this one. We'll look at this one because I want to show you the method again. And I want to show you that infinity minus infinity is indeterminate. And who knows what the answer might be. It was 0 this time, but you know, for a problem that's the same form, might get some totally different answer this time. All right? So, okay, here again is the form infinity minus infinity. 1 over x, as x goes to 0 from the right, that will be infinity. So will this. E to the 0 power will be 1. This will look like 1 minus 1. It'll look like that one. It's of the form 1 over 0. This bottom part will get incredibly small, close to 0. 1 over that will go to infinity. So it's still of that form. So let's use the technique. Well, what was it? We'll combine these and see if it's an indeterminate form there, and then we'll use L'Hopital's rule. L'Hopital's rule, which says once you have an indeterminate form, take the derivative of the top and bottom individually and then reapply the limit. So I'll get this time, if I subtract these, I'll get e to the x minus 1 minus x over x times e to the x minus 1. So there we go. That's subtracting those two fractions. What does this look like? Is this an indeterminate form? If I put 0 in, I'll get 1 minus 1 minus 0. So, okay. This right here gives me 0 on top. What about down there? 0 times 1 minus, also 0 on the bottom. So it's an indeterminate form. I can use L'Hopital's rule. That's why I took these and combined them. All right. What does L'Hopital's rule say to do? We take the derivative of this top portion, this top formula, whatever it is. It would be e to the x minus 0 minus 1. And then the derivative of this bottom part, I'll have to use the product rule on that. F prime is 1 times e to the x minus 1. F prime times g plus g prime times f. It'll look like that. Okay? Now let's reevaluate this limit. What happens as x goes to 0 from the right? Well, okay. So e to the 0 power is 1. 1 minus 1 is 0. And then down here, 1 minus 1, and then, it's still indeterminate. Okay, well, that's the way it is sometimes. All right, one more time. Hopefully this is it. Limit x goes to infinity. Because this is still an indeterminate form, I will reapply this limit to e to the x, which is the derivative of e to the x minus 1, over e to the x, derivative of 1 is 0, and then I'll have to use the product rule on that, which will be like so. F prime g plus g prime f. Okay, so that all looks good. And then now we'll apply the limit to this. Hopefully not get if we get an indeterminate form again, I'm giving up, all right? But so, okay, hopefully it works out this time. 0 goes in here. E to the 0 power is 1. All right. And then down here, 1, 1, 0 times 1. 1/2. All right. All right, so now we see it. Infinity minus infinity is indeterminate because, well, here we saw infinity minus infinity was 0, but here we see it's a half. That's what we mean by it being indeterminate. If I could guarantee you that it was always this one certain answer, it wouldn't be indeterminate. It's indeterminate because who knows what you might get. But here you see the technique to figure out ultimately what it is.